Okay, good morning to our next lecture. We were looking at the potential yesterday, and I started to um, show you some example, and then we just actually got started to um, get the first line where we had the problem set up. Let me just pull up the slides. Oh, okay, that should do. So we had an electric field. This is given as an electric field where the x component is actually k times y, so it is y dependent, while the y component is x times k, so it is x dependent, and the Ez component is actually not present, is vanishing. So you have to assume that, and I tell you this is a viable electric field and an electrostatic field. And now we want to see what the potential of this is. And we introduced the potential function last lecture. And you know, the E field is related to the potential function, which is a scalar function. So it is the electric field, the electrostatic field is a gradient field. That means you can obtain it from the gradient of a scalar field. So that applies to the electrostatic field. Just maybe an outlook, because we will not get this advanced into the electromagnetic topics. But in addition to that potential that we have been introducing for the electrostatic field, there's also a so-called vector potential, which you can use to obtain then the electrodynamic field. And the total electric field can then be obtained by the combined scalar potential and the vector potential. What we are looking at here is only the potential, the scalar potential for the electrostatic field. So now the quest here is calculate the potential function. The reference potential is 0, and it is 0 at the reference point, of course, and that is located at the origin, which is 0, 0, 0. And we have a Cartesian coordinate system, and we want to first calculate the potential function, and then we want to also draw the potential function. So just as orientation, we have here, we are looking at a Cartesian coordinate system. And here, within that space that is spanned up by that coordinate system, we find our electric field, and we also can define here the potential. And our point 0 is here in the origin. That's P naught or P0. And how do we obtain the potential? So the reference potential, I have plotted it here, but the potential we said is obtained by, and it is a function here of R, and it is obtained by taking here the reference potential that in general, we can set at an arbitrary point and give an arbitrary value. And then we integrate from that reference point to the point of interest, that is P of R, and we integrate over the electric field. I skip here the dependent, I mean, of course, the electric field is dependent of R, the bracket of R I just left here, but that's understood. I left it out. And that is what we have to solve for. And let's say our point PR is somewhere here. That is given then with some X and some Y coordinate in this specific example. So we have to integrate somehow from point 0 to point P. So how shall we do that? I mean, we could do it like that, but actually we said it doesn't really matter the path of integration because we have the electrostatic field being a conservative field is in the end irrelevant. We can pick an arbitrary path to integrate as long as the start and ending point remain the same. So we can also integrate along this jiggly line here, and this will also give us the valid result. Well, but the question is what is easiest for us? And for this specific problem, this very curvy line here is not very convenient to integrate. So we could also, with this it is so perfectly legitimate, and as it turns out, also advantageous to use a simpler path of integration. And that is what I draw here in this purple color. We first move along the x-axis, and once we have reached the x value of our that corresponds to the point we want to integrate to, then we only move around in y direction. That means we split up our integration path in two segments, and we call the one here C1. And basically, we can have that here. Yeah, this we call C1, and this we call C2. And this here, this point here is x0, yeah? So we integrate first from 0, 0 to x0, and then we integrate from x0 to xy. And yeah, let's do this. Let's start with the integration along C1. So we have to look what is our path element here. That is our dr. And this, as you can see, is now only going in x direction. So that Ex, remember, is the unit vector. Or if we write it in x direction, if you write it here as in column form, it is 1, 0, 0. And then the second step is the integration along C2. And here we only integrate along EY. That shall be our element. So EY is then, of course, the unit vector. Here, maybe I want to add that comment here that the integral over the electric field, it does not depend on the integration path. It does not on the integration part itself, it only on the start and end point property of the conservative field. And that means we are free to choose this path. Okay, let's get back to our integration. So we are using now the xy coordinates, and we have this 0 that we have decided according to the problem description that the reference potential at the origin is 0. And then we integrate from P naught to Pxy over the electric field along the line element. And now we enter these line elements. The reference 0 I can drop here. So we have minus, and we first integrate over the first line here, right? So this is from 0, 0 to x0. So, right, so this is our first step from here to here. And what is the electric field? Here we have that is ky times unit vector of x plus kx times unit vector of ey. Okay, so I denote it here now with this y prime because this is the running variable we are integrating over, while I denote the y unprimed basically as our destination point, right? So this will be, and also for the x, this is a point we are integrating to. The running variable under the integral here is then primed. Okay. The set component is vanishing. We drop that. What is our line element? Well, the line element is actually the dr is this one here. So we insert that here. Yeah. And this here gives us now our first contribution. I mean, technically it goes all the way here. This is the first integration path. So we are not done here yet with, we have to add also the second, meaning the second component here is still goes here to the phi of xy. Yeah, let me. So again, we have to integrate this time from this point here. Actually, this is where we ended C1. So that's the starting point of C2. That is x0. And the end point then is xy. So we integrate. What is the electric field? Again, is of course the same formula. It is again ky prime ex plus kx prime ey component. And now what is our line element? This is this one here. So you insert that here, and then you have ey delta y prime here. So the phi of x and y, now when we integrate, we see here the line element here in the first contribution to the integral. Basically the contribution due to the path C1. You see that the line element is oriented along x direction. We have here only components of the field which are aligned with Ex are contributing to this integral. So you see that second, what you have here in the bracket, the y component, that actually doesn't yield a contribution in this first integral. So we can simplify and see that we have to actually integrate here from 0, 0 to x0 over k times y dx. Mind that the potential then becomes a scalar field, and it doesn't have any vector properties. So the second integral, this, which is here C2, that the integration path runs, the line element is perfectly oriented. That is by our choice, because we said we first go along the x-axis and then we go at constant x up the y-axis. So this here yields in this integral only a contribution for the components oriented in y direction, which is the second one here in the bracket. So this becomes integral from x0 to xy, k times x prime over dy prime. And that we can integrate now. So what is k times y integrated over x? Well, that is basically we integrating over a constant 1. So the integration yields here k y prime x prime. And for x, we have to insert the starting and end points, while for the second integral, we are integrating over y prime. Now, this gives us kx prime y prime here, integrating from x0, the end start point, to xy. Now let's insert, and you get here for the first partial integration, no, partial integration, first partial path that we use for the integration. So that is beginning point, the end point is x equal 0. So this gives us just 0 in the beginning. X is also 0. Sorry, in the beginning, x is in the end point, x is not 0, but the y is 0. So that gives us 0. And the starting point, both of them are 0. So also there we only get a 0 contribution. And for the second, we have the endpoint. We have x and y. So we write k, and the x prime becomes x, so y prime becomes y. And for the starting point, well, the y is again, the y prime gets 0, so we are here. So in total, we get our potential, which is okay. Now let's take a look how this potential looks as we plot the potential function, or as we sketch it rather, to see how what can we expect from that. So let's sketch the equipotential lines. So what are the equipotential lines? Well, these are the coordinates where the potential is constant. I mean, in the two-dimensional scenario, it gives us lines. When we have the three-dimensional scenario, and you could argue we have here a constant no variation in y, so you can actually extend in z. We have no variation for the z coordinates, so you can extend all that into the z range. Then you don't get lines, you would get surfaces. So we have computed this minus k times xy, and this has to be c, where c is some constant. So if you want to make a sketch of these lines, so you need to relate how is y in relation to x. So that is quite simple. You have here that equation. This is constant. You look y dependent of x. So you just bring that over and you say y is the constant over k times x. Now let's plot that. So let's see how it looks in the first scenario. I mean, basically, look here at the different quadrants of that plot. And here in the first case, we have x is larger than 0. We also have a constant which is larger than 0. Then we get lines here. They roughly run like that. And in the second scenario, we have also x larger than 0. We have a constant c smaller than 0. Then you get equipotential lines in this quadrant here. And in the further case, which I label as 3, you have x being smaller than 0, the constant again being larger than 0. That gives you here some lines. And in the fourth case, where x is smaller than 0 and also the constant is smaller than 0, you get the lines. And of course, they should, I see that in every quadrant, they should roughly look the same. That is not so perfect right now. So the electric field, how would the field lines run? So one thing is we know, and we have also stated that is actually, I mean, that's inherently like that the field lines run such that they intersect with the equipotential lines at a perpendicular angle. So that allows us to plot here the electric field, which is ky, kx, 0. So here you notice that, first of all, for x equals 0, we are on the y-axis, and we have E equal to k times y times ex. So we have on the y-axis only an x component. The y component is 0. And on the other hand, for y equal to 0, that means while we're moving along the x-axis, we have ex 0, while the ey here becomes k times ex. So our electric field here then basically is. So for the field lines, you obtain such field lines, and you have to make sure they intersect here always at a right angle. And here we also know that one component is vanishing. So you have all these right angles here. These are our field lines. So along, if we look at this one here, then here you only get, if you make the field vector in here, they only on the x-axis have component in y direction. As you increase the x, the magnitude is increasing as well. And yeah, for the y-axis, you have a similar meaning. Also, if you make them in the potential lines such, the equipotential lines, the way that you plot them such that you have them spaced equally, then the lines become, the spacing of the line becomes more narrow as you move out from the origin. Okay, do you have questions on this?
This is just an example you give me.
This one here?
Yeah, it's just an example you give me.
This is a specific example. So this is
So it can be kx also, right? Kx, ky. It can be kx.
in which part here?
You give this example for E, but it can be. It just depends on the question.
Do you mean why is this? Does it look like that?
No.
Or
Your question is ky, kx 0.
okay, you are, okay, yeah. So this is a example just picked where we can demonstrate. We could check whether this is also working. You have to also, of course, verify. You can pick any description of an electrostatic field, but you have to verify though whether whatever you put in here is also representing a conservative field. So that could be, if you make some random selection, it could be also that you pick something, happen to pick something which is not conservative, and then it would not work.
Okay.
So that is something you have to check whether it qualifies for that. But if it does that, then you can, yeah, you can pick an arbitrary other function too. Okay. On Tuesday, I think, or was it on Monday already? I had also made some wrap up where I summarized important things that we had written up, which we had discussed this far. And I actually hadn't posted it online yet, but I noticed that it wasn't posted. You find that actually online in the meantime. And also here, because also the question comes, which equations are in particular important. So, well, those that I have put in these wrap up that are highlighted in these red boxes, these are certainly amongst those important ones. And I want to maybe continue on this wrap up what we have done this far and summarize some more important takeaways. So about the work. So this is summarizing some again. I continue to summarize some of the things that we have discussed. Work in the electric field. So general, what how's mechanical work being defined? So the work is W, and it is obtained by taking the integral over the force field over a given path. Sorry, this is in R here, yeah? So the path is defined by Cp1 to Cp2, and we have seen that if you have such a path here, which is of random shape, then you have here in this force field some force vectors, and you have to integrate taking small segments along this path, and these segments here are basically tangential to that path. And when you integrate over the force fields, the contribution is here only by the component of the force. So this is here a vector, right? That is aligned with the tangential component of that segment. So F is our force field, and the force is varying locally in general. Yeah. That means it is varying by both by magnitude and by direction in general. That curve that we choose for integration can be arbitrary. And we calculate then the path integral, the path, or respectively a curve integral. And we have discussed that we are doing these three steps of first parametrizing that path using this parameterized version to parameterize also the force. And then we adjust the line element, where this one here represents the tangent vector. And this is then for the electric work, of course, the same. We also integrate force over distance, over the path. But for the electric work, you have to consider that our force is given by the charge and the electric field. And so we can write our formula for the work is Q, that is the charge which we are moving through the electric field from P1 to P2 over the electric field. This is 1.7. Okay. Then we also have discussed the electric voltage. What is the electric voltage? The electric voltage, the formula for that is U12 W12 over Q. So this is basically the work per charge that you have to bring up, and that defines our voltage. And 1 and 2 are basically in this particular scenario the starting and end points from where you move to the charge, starting P1 to P2, you integrate over electric field. This is our formula 1.8, and you see the voltage is just obtained by integrating the path over the electric field along the path. So it is we have removed because it is normalized work per charge, so there's no charge occurring in that formula then anymore. The dimension for the voltage is 1 volt, which is joule per ampere times second. So we have discussed also properties of the electrostatic fields. So electrostatic fields, and because I said earlier, if we are in any given moment, you always have only one electrostatic field. There's not a multitude of fields. When I say fields, then different realizations or different at different instances. But if you solve for a problem, or if you look at one scenario, you always have one electric field. You don't have the electric field from charge 1 and the electric field from charge 2. You have a contribution from charge 1 and from charge 2. It adds up to a single electric field. So very important, the electrostatic fields are conservative. Now, I always make this tilted. And okay. What is a consequence, or respectively, by what criteria can you tell that the electrostatic field is conservative? So that means that the path integral depends only on a starting and end point. That means, in other words, the integral is path independent. So And mind, that means this is true for the work as well as for the voltage then. So from P1 to P2, integral over the electric field is path independent. Also, this implies that the closed loop integral is vanishing. Closed loop path integral is zero, meaning this one, this formula holds true. This actually is relevant for the Kirchhoff voltage law, yeah? So we have discussed this. KVL for Kirchhoff voltage law in circuit theory. That is a energy conservation law. And this conservativeness of the electrostatic field implies, or vice versa, you see it if it implies that the curl of the electric field is zero. That also means if you are in Cartesian coordinate system, that the case component of the electric field derived with respect to the J component is the same as the partial derivative of E sub J, partial derivative with X sub K. Or, I mean, this is basically if you take the curl operator and you look at the components for every component, it has to vanish. So you can also write that here like that. And that is also basically coinciding with the integrability condition. But mind, this here, the curl vanishing, this what I also, that you might also find rotor. Also, you can, you know, instead of curl, you can also have rot for rotation. But this one here, this here, that is universally valid. But this formula here, this is only applicable for Cartesian coordinate system, because you can see in the formula sheet that I've given you that the curl operation, I mean, this is a universal, this is holds always, but if you execute that basically on an electric field in a different but Cartesian coordinate system, then these expressions, this is not what comes out there. This is a applicable here, this what you see for Cartesian coordinate system, but that's that curl operation, of course, that's holds true for all operations, for all coordinate systems. So only in Cartesian coordinates, this one here, this here, everywhere, curl A is zero everywhere. So I mean, independent of coordinate system. Further important takeaway also from what we have discussed in the last couple days also is the electric field is a gradient field, and that points us to the electric potential. Because it is a gradient field, it can be obtained from the gradient of a scalar field. So important, again, this potential is scalar. So the phi of R that I've put here is the electric potential, and the phi of R is a scalar field. While you obtain the electric field from that scalar potential, of course, the vice versa is also true. You get the potential from the electric field. So it can go back and forth, but there's a small difference because the electric field is uniquely defined by the gradient, I mean, by the potential, by the electric potential, while the potential from the electric field is not, well, it is, you still have a constant, basically. It is defined up to a constant, which you're free to choose. So you obtain this here from this reference potential at a reference point R naught, and integrating here and subtracting the result from the integral starting from the reference point to the point R over E dr. So PR is an arbitrary point in space, and PR naught is also the point P naught is a reference point. Important takeaway also that the E field lines the E field lines and the equipotential surfaces, they are perpendicular to each other, yeah? That is what we have seen also in just the example that we just plotted and also what we discussed yesterday. Equipotential surfaces is general if we are in 3D. They are perpendicular to each other, meaning that the gradient of the potential is perpendicular to the equipotential surface, or you can also call it isosurface. And for the Coulomb potential, this is actually the potential you obtain from a single charge. Okay, this is a wrap up of what we have done the last few days also. So leaving out some details, but these are some important aspects that you should, again, also take along. So we are about to move to chapter 1.5, but before that, I want to also insert another of our math recaps, which we have maybe also partially used already, but I think this is nevertheless quite good to have that in here now. And then, do you have questions on this here, what on the wrap up? Otherwise, I suggest I'll start now a bit with the next part of our math recap, and then afterwards we start with 1.5, and maybe in, wait a moment, how far we are in now? We have till 12:30, right? So maybe in 15 minutes or so, then we'll make a little break, or shall we do it right now and then start with the? Okay, let's make 10 minutes break and then continue. I try to be punctual with the 10 minutes this time because I think And other days we got carried away a bit with these questions and so. Okay. Okay, let's proceed. I have this sign-up sheet also. I'll start to pass it around. You, please. Thank you. Let's do some recap on integration. This is one recap, and then there's also a further recap where we also look a bit more into the aspects when we have different coordinate systems, that then also in particular different than Cartesian. And these things we will increasingly need right now. So I think it is a good time to bring those in now. And I want to first, look at integration in space, also in the three-dimensional space, integration over scalar fields and over vector fields. And there, let's start with the more basic example where we have an integration here in one dimension first, and then we do the volume and then the surface integrations. So if you have here the example of one dimension, then we have here a plot of a function, which is over x, and here the function of x. Then this function will show here some kind of development, and you want to integrate from x1 to x2. Then you see what is under, basically you segment here your function into small pieces here. This here is your delta x. You make a variation. You can evaluate the function at x1 and at x1 plus this delta x, and then you get a variation also in the function value. And that occurs from point to point. There's always a, as you move with the delta x along the function, you have also a delta f in the function value. And you basically, the idea is that you want to have the area which is here in dashed here. You want whatever is under the function curve, and you want to have that from x1 to x2. You want to have a value for that. And in order to get a more accurate estimation, you evaluate the not only the function at x1 and x2 and take the mean value out of these two. You do that at a multitude of different x's, and you space them in delta x. You let them increasingly go to smaller and smaller values. So you make your delta x become in this infinitesimal delta x, and so you transition from this still discrete approach that is sketched here in the picture to a continuous variation where your function x is given here is not evaluated only at these discrete points, but in a continuous fashion. And you have a summation of all these contributions. So this is basically um, originating from taking a sum of different function values into this continuous regime that is your integration in one dimension, right? So this is here the f von x is a scalar function, and if you have that in multiple dimension, then your f becomes a function of x, y, and z. Sorry. So then it's not just a scalar function, then it becomes a scalar field. So then you want to do things like volume integrations, and for that you have here an x, y, z coordinate system. I've plotted in here some kind of element, and you want to assess the volume integral. So your function again is this function of x, y, and z. In this particular plot here, it happens to be 1. It is a scalar field, and we can evaluate it here for x from 0 to 4, for y from 0 to 2, for example, and z is running from 0 to 1. So these are the boundaries of this cube here. Not this cube, but this block. And you are looking at the volume element, then that corresponds to having a integration with 3 line elements. You use dx, dy, and dz. Yeah, so this dv corresponds to the product of dx, dy, and dz. This is your differential volume element in Cartesian coordinates. And so you get a volume integral here over this scalar field. You take the differential volume element. You see these are the boundaries here. It goes from 0 to 2 in y direction, 0 to 4 in x, and 0 to 1 in z direction. So you integrate that. You can also write that here as a volume integral over t to the 3r of that element. But as you see, the alternative way of writing this volume integral is that you basically split it up into the 3 differential elements. You have that one running from, the function value is 1. You take the dx, dy, and dz, and according to what your differential volume element is defined of. And we have said what the integration orders are here. That is for x, it is 0 to 4. For y, it is 0 to 2, and 0 to 1 for z. And then you can integrate one by one. You keep the outer 2 ones. You start to integrate over x. 1 integrated over x is basically x. These are your boundaries. What remains are your integrations over dy and dz. And this here is your differential volume element. You keep going on. You insert the boundaries from that first integration over x. That gives you 4 minus 0. So this is 4 dy and dz. You perform the next integral step. That means you integrate over the y component. You leave the z here, and that gives you 4 that remains here times y, the boundaries for y are from 0 to 2, dz, and then you integrate from 0 to 1. You insert the boundaries here in, you have performed the integration over y, over the y component, but it was only 4. So you have here in the bracket 4 times y. You insert the boundaries, so y is 2 and the beginning point is 0. So yeah, it is given a very simple problem, but this is basically the procedure how you go about. And then you do the last step of integration over z that gives you here 8 times z from 0 to 1 is 8. So you have taken this qubit shape here, and this is your volume here of that cube here. So, for example, now if your scalar field here was a mass density, then what would be the result? If this here is a mass density rho sub n or sub, yeah, so this here is a rho. We had that earlier. This is rho. We use it for densities often. Sorry, now I have given you the rho with the rho. It is a RHO, that's a Greek for R. And it is commonly used for densities, like you have it for mass densities, but we also will use it for charge densities. So let's just assume that this is 5 kilogram per meter cubed. Then what is the result? Well, the result of the volume integral then is a mass, because you have these line elements, each has a unit of length, for example, in meters. And if you take these 3 line elements, then you get meters cubed, or the volume element is also in cubic meters. So multiply that. The result of the volume integral would be then the mass. Yeah, you integrate the density over the spatial density, and you perform the volume integral over that, so you get the, in that particular case, the kilogram. But this right now we had a very unattractive function in that sense that it is a scalar field, but it was only a constant. So of course your function here can have any other shape. It could be, for example, something like reasonably a function of x, y, and z. So it could be something like x plus y squared plus z. So it can be any general function. Okay, there are of course some conditions to be considered, like whether it is integrable also. There should not be any instances where it might go to infinity or so, that you have to consider whether a function is integrable. For that, you have, for example, have this integrability condition. But in general, if you have an arbitrary function, you can attempt to integrate it. Now you can also perform the integration, instead over the volume, over the surface of the cuboid. Surface, basically, now we integrate it over, let's look at this surface here. That would be the top surface. Then we do an integration over the surface, and the top surface here is colored in red. Then we take the integral over x, over f of x, y, and z, and we only take the surface elements here. In that case, you see this surface is top surface, is aligned in the xz plane. So we only use the x and z elements, and the cuboid is given from for z 0 to 1 and for x 0 to 4. The function is 1 here times dx times dz, and that we can also then denote as dA. Yeah, and then you are already at the step by step. One element of the surface, I mean one dimension here, you get x from integrate over x. You get x from 0 to 4. dz remains to be integrated. This is 4 times dz after inserting the boundaries for the first integral, and then the second integral solved. So you have 4. So this here is your scalar differential surface element. So now, what do you do when you have surface integral? So there it becomes also interesting because we also differentiate between surface integrals in scalar fields and surface integrals in vector fields. So what you've seen above was also in the scalar field. And for scalar field, it is basically also like the volume integral, but you do it in 2 dimensions. So surface integral over the function f of x and y. And then you just replace basically the differential volume element dV with the differential surface element dA. This is just what we have done here for the specific example, but here to write it in more general form is, instead of going here over a volume element, you do here a surface element. So volume is always commonly denoted with a V. Here we have a surface element of a scalar function times the surface element delta A, and in Cartesian coordinates, this volume element could be Cartesian coordinate system, yeah. This could be dx times dy or dy dz, yeah, dx dz of course also. But so this is just a refresher on the how you go about these elements. So if you have these surfaces aligned here, like we had in the case of the cuboid up there, then these are exactly the elements that you get. So on the top surface here, if you have such a cuboid, it is parallel to the xy plane, right? Xz, xyz. This is our right-handed coordinate system. You can use the right-hand rule. You have Ex, Ey, and Ez. You see on the top here, top surface is parallel to the xz plane, so your element is dx dz. On the side surface, which is parallel to the xz plane, sorry, it is parallel, surface parallel to the xy plane, that would be here in the back, and in the front, that would be, of course, xy, and surface, the side surface, that would be parallel to xz. Then accordingly, you take dx and dz and so on. Yeah. And a bit more tricky it is if you are then in other coordinate systems also. Now it is very easy also because the surfaces align with the orientation of the unit vectors. But if that is not the case, it might get a bit more intricate. But in particular, if you have other coordinate systems, then you have to take into account the scale factors. And this is something quite important that I will go then a bit also in our next recap. And that will be also the final recap. And you will encounter that now. You have maybe started to encounter it already a bit. But we will need that soon when we are solving some of our problems. But there are not so many cases. I mean, there are potentially a lot of cases, but you will see for the problems that we are running into that is also limited, the number of cases that one has to master. But then in the end, you can look those all up in your mathematical formula, either in your mathematical handbook, respectively. I have collected you for you some in this data sheet, which not data, in this formula sheet, which I have uploaded. So you have to make sure that you take into account scale factors, which come from the coordinate transformations. And so I, in general, want to refer you here to the mathematical handbook, which I have also named some, like the Bronstein. In the beginning of the lecture, you find those also in the slides, but you probably also have some mathematical handbook. So don't forget about these transformations. When you're not dealing with a Cartesian coordinate system, don't forget to take these scale factors into account. Very important. What we are also encountering often, so we have now said we have volume integrals, we have surface integrals, and for the surface integrals here, we used for these, like for the cuboid, this top or bottom surface. But what you have also often is that you have closed surface integrals. And the way they are denoted commonly is that because they are enclosing a volume, we denote it with this partial V sign. So often we are, sorry, this is, we are, or we are using, or we use, often we use closed surface integrals. And this will come up in the next chapter now with our Gauss law. We often use closed surface integrals over V or volume integrals over volume V. So here you have then the second scenario. So the first scenario, you are covering basically what do you do when you have here scalar fields, and the second is you have vector fields, and then you're interested in the flux integral. Basically, there you see a small picture of the river that we have in Munich. So you have water flowing, and you want to know what is the flow through a certain surface. That would be a flux integral. And now you, of course, can, if you have a flow of particles, you can assign to every particle a velocity. So that means it has a certain magnitude and a direction. And when you, however, interested in what is flowing through the surface, what flows through here, like you see in this picture here, then the contribution comes only from that component of that velocity vector that is perpendicular to this surface. So if you use some um, flux integral, then what you do is that you project the field vector to the normal vector of the corresponding area. I mean, that I think makes very much sense. If you look at it, this is the area you want to evaluate your flux integral over. And then if that flow of that particle, if the velocity is somehow in an arbitrary direction, to really count the flow rate, you need to take the component that is really normal to that surface. So basically, you project then the vector field within this area onto the normal, and that gives you your flux contribution. Do you feel comfortable with that? What do you say? We had that also, this projection, um, with the work integral, where we projected even though it was a one-dimensional integral, we projected the vector onto the path of integral to see what part of the force vector is really contributing to our work. So we project the field vector to the normal vector of the corresponding area. You read that? Area. So this is our velocity vector. This is the area where we want to compute the flux through. This is a normal compare. So this is the surface element of the surface, and this is a normal vector to the surface. Then this is a flux of velocity. So what the example I gave you here is a river and the water flowing through. Any water particle can have arbitrary direction and speed, and you see what flows through this surface. Flux of water, the example here. Now, also interesting is here what you see on the left. This is in particular interesting for us. You have here in the center the charge, and you have an enclosing surface, and you have an uh, electric field which is originating due to that charge in here. And when you enclose the surface, this is just a virtual surface. It doesn't really have to be an actual a physical realization of any object or so. It is just a virtual surface, and you want to get here a flux of the electric field. So like in the left-hand example, you have actually a flow of particles, and these particles at any given moment are described by a vector field, which is a vector field of velocity. Now you also have a vector field of that electric field, and you can give a flux of the electric field through this surface. And in that instance here, you have actually a closed surface over that sphere. So when you look at this, you have here you have here some surface element, and at this element you have here an electric field A sub j, and you want to now get the flux of the electric field. Thank you. So here you have EJ, and you have a normal vector on this element. Maybe I should plot that in a different color. This is a normal vector on the j's element, or you can also give, yeah. So you have here this surface element, you have a normal vector to it, and then you see what is your contribution. You have here, you have here, you have here, you can define a element here that is composed of the surface area of that particular small element here, and the normal vector that we denote here with the a sub j, the vector, and then you get the flux through that particular element by taking the field a sub j that is located at this element j times this element, which is basically obtained from the value of that, the area value, or the surface value of that element, and given a vectorial quantity from the normal vector. So that is the absolute value. And in particular, this case here, because we have this as a concentric sphere over the charge, it becomes actually convenient because aj is parallel to the normal vector. So cosine alpha is 1. We can get the flux through aj by the cosine alpha is just 1, and the aj itself, that corresponds actually to this delta surface area, so the dA. So basically, you take here small segments of the surface, and you look at the normal component of that surface, and then you see what kind of angle you have between the normal component of that surface and the flux quantity, and only or the electric field quantity in the specific case, only that component that aligns with the normal component contributes to the flux integral. So, or to show that here, maybe a bit in more detail here, this is basically what this graph shows here. You have here, this is a cut through the surface. This is a surface, you just see a cut through it. This is an element of the surface, so you can think of this extending into the towards you, like that we are having into the space. You're looking crazy onto the cut, and this area here, this actually signifies here a surface element, a differential surface element. This is your normal vector, and whatever the flux or whatever the force field here, or the electric field here that we are looking, whatever it is given, you project that here onto the normal vector, and that will add to the contribution of your flux integral. So you do an integration over the surface, over the vectorial field. You take here, it's this time it is denoted as a capital N. You often do it actually with a small n. And you weigh it also with the area element. So that these two parts actually you can combine here as d of dr vectorial. So this is what this notation really signifies. So you have here vectorial differential development. And then what you also have to consider is that for different coordinate systems, that has to be again adjusted. Then I have to refer you again to the mathematical handbook and to the sheet that I've given you. And that is coming up now. That is Gauss law, just as a, there you do a surface, closed surface integral over the so-called displacement field. And that is coming up now. And the uh, closed surface is signified by this symbol here, this kind of this partial symbol, and the V. This is basically here a closed surface enclosing a volume, meaning you have here such a sphere, and this, sorry, this whole sphere is with a given volume, and just the shell here, so just this surface, that is signified by that symbol here. That's a shell. Okay, this is a quick reminder on how to work with the integrations on the different dimensions, and what if you have to deal with flux quantities, then we need to do this projection. You have questions? Or if the questions come along as we use these things, then please don't hesitate to ask. Okay, then let's get back to the maybe a more exciting next chapter, and that is about polarizability of materials. You have a gap text also for that. I pull it up. I have actually this has been up for a couple of days, but I've updated it yesterday in case you wonder. But it's, if you use the old one, it's also fine. There's not, it's just some minor beauty corrections. So we have electric fields in polarizable in materials. So for that, okay, we want to look at fields in polarizable materials. And for that purpose, we have to look first here a bit at some examples and where we need that, and how the how it actually becomes interesting for us or relevant for us. So first example is here. You have here a capacitor. This is a special example of a ceramic capacitor. And you know, the basic concept of a capacitor is that you have two electrodes. And also here you see electrons. There's a ceramic disc in the center. And this basically separates this one electrode from the second electrode. And the capacitor is used to store energy. That is amongst one of its purposes. But the dielectric material here has significance because it is determining, amongst other factors, but it is a very crucial factor for determining the amount of energy that can be stored. So that would be one reason why we are interested in the polarizability of materials. So we have a capacitor that has two electrodes, and we have here one electrode. We have here the second electrode. We have the one charged with a positive charge, and the other one is with a negative. So you basically have here a small number of charges, or a large number of charges, ideal. So you have field lines, as we had discussed earlier. They are expected to be homogeneous within these two capacitors. You have within these two, between these two plates, you have here some connection where you can charge up the plates or discharge them. And what you have also is some kind of filling in between, most likely. I mean, it could be also just some vacuum, but that is actually not the not likely scenario. So there will be some dielectric materials. There will be some material which is not conducting. So this is some material, some already just to keep them at distance, you need some material in there. But this material is a dielectric material. So it is not conducting, but it can be polarizable. And what advantage does it have? It basically enhances the capacitor's capability to store energy. So if you have the select your material well, then you can store in the same volume of the capacitor more energy. So that would be an example why we are interested in the polarizability of materials. It can enhance the capacitor's capability to store charge, enhance energy. So a second use case is, in the end, this is also a capacitor, but here we have a very special material between the electrodes. So you see this is kind of interdigitated capacitors. You have here plotted in red here the electrodes, and you see there's one electrode, and there this is a B, and the second electrode A here, and these are like fingers that hold into each other. Hence, also the name interdigitated, from digit, the finger or the finger segment. So they are kind of grabbing into each other. So advantage is by having such an interdigitated design, you increase the interaction because you have in order to get a lot of capacitance, it is good if you can bring as much as possible of these two electrodes in close contact to each other. So now you have enhanced that interaction surface by making it interdigitated. And so you have one electrode, and you have the other electrode here. And again, you have, in the essence, however, even though it is interdigitated, the interaction is still described by these two electrodes which are having charge on it. You have your field lines, and now something interesting is happening. You have here there a gas sensitive material, meaning the filling here is a gas sensitive material. I mean, in this interdigitated design, you not only use for gas sensors, there are a lot of other applications. This is the interdigitated design is meant to maximize the interaction possibility between these two electrodes. I mean, to maximize, if you look at this parallel plate design, that would correspond to making the plates very large, and this is kind of workaround how you can make a large interaction without having necessarily to increase the size of the capacitor as much as you might have, because yeah. So, and this here is now a gas sensor, so it has a gas sensitive material, and in the presence of the gas, the dielectric property of that material is being altered, and as a consequence, the capacitance of the capacitor itself is changing, and you can measure that. So you basically detect a change in capacitance, and it tells you that there's some gas present. So as a consequence of this change of property, you measure a change in capacitance. Further example, you have here some capacitive silicon microphone. So, oh, sorry. So you have the gas-sensitive material, and in presence of gas, the material is changing its property, and you notice that. Further example, here you can also, the change of capacitance that can be also used to detect sound waves. You have here a small capacitive silicon microphone, and you see here a sketch where you have a backplate and a membrane, and basically these are the two plates of your capacitors. As you have some pressure wave entering here, that case the membrane is deflected, and the separation changes between this membrane and the backplate, and inevitably the capacity changes. So the capacitance changes an immediate indicator for the pressure wave, so you can use it to capture the sound. So we have a capacitive device here. We have two electrodes, and one of them is movable. If you plot that a little bit, then you have again here these two plates, electrodes. One is a membrane, and you have that made from silicon. You have here some silicon, then you have silicon oxide, and then some silicon nitride. So that means so inside there's the E field, and you have on the one hand oxide, you have nitride, and you have air. So you have different materials to consider also. Also here you have capacitive aspects to consider when you have such a MOSFET. You have here some silicon oxide here. So this is a structure of a MOSFET. I'm not sure how much I think that is probably something still to come. That is also not really part of the lecture here, but this is when you get into semiconductors. You have here, this is the design where you have source, gate, and drain, and you have here the different dopings of the silicon, and there you have also inside that transistor structure capacitive layers also that are forming, and so yeah, that is also relevant here in the broader picture. So you can classify a materials according to their conductivity, and you basically can say there are three types of materials. The one is the conductors, which are, for example, metals like copper, silver, or platinum, aluminum. So you have, and then on the other hand, semiconductors, and you have insulators. And the properties and how they're conducting is very different. Of course, a conductor is signified by that it's conducting very well. So these are metals, like, and what does conducting well mean? These usually have, you can specify the mobility of electrons in there, and how many of free electrons you have uh, per volume, so to say. So you have here around 10 to the power of 22 free electrons per cubic centimeter, roughly. This varies, of course, with material. It varies with the special conditions also, what the temperature is. But on that order, you're there you're in. That means these electrons that you have are in particular also highly movable and can contribute to the charge transport. So they conductors are, as the name implies, very good for conducting. So these metals are very good conductors. And I want to refer you then to chapter 1.7 coming up, where we look at the conductivity and how to quantify it, how to work with it. Semiconductors are different in that sense that semi means half, so they are kind of half conducting. You know, semiconductors are such thing materials as silicon, gallium arsenide, for example. That could be pure silicon. What is their conductivity, or what is their number of electrons per cubic centimeter? There you're in the range of 10 to the 10. It's not a good conductor. And you can, however, also affect the conductivity by doping the material. So you kind of you break up the ideal crystalline structure of that semiconductor, and that can add extra charge carriers into the material. You put charge carriers in, and then you get to 10 to the 15 till 10 to the 20, still 2 orders of magnitude slower than the conductor. And then basically you can tailor the conductivity. But it is actually a bit more complex. So this is, however, not the topic of our lecture. But in general, it is also interesting maybe to keep in mind, if you have a conductor, it gets increasingly better in conducting as you reduce the temperature, ideally all the way down to a few millikelvin or so. The cooler the conductor is, the better it is in its conductivity. While for the semiconductor, this is not the case. You cool the semiconductor down, and it is getting actually worse because you have no free electrons then anymore. And I have to reduce this a bit in size here. Oh, I'm over time? Or no? Okay, not. Pure silicon. Why, I don't know why this extra line entered in. Hmm? Let me. Um, this here is doping. Below. Sorry, above where? Carriers. So you can put charge carriers in by adding some doping. So you modify, and of course, then it is also um, sensitive to the temperature, sensitive to uh, what potential you apply there. So this semiconductor is in that sense in between, but yeah. And then you have the insulator, and these are the dielectric materials. This is what we are also interested now. So they have no or almost no free carriers, no free electrons. So for any materials, of course, you have always electrons. Every atom, every nucleus is surrounded by it is by atoms, which is compensating also the positive charge of the nucleus. But the question for the conductivity is whether these electrons are free to move or not. And so in the dielectric case, you have essentially no conduction, so they are not conducting. And that could be, for example, things like silicon oxide. This is also silicon nitride. These are also ceramics. So we are now looking into the dielectric materials. So they have no free electrons, so you have no uh, um, conduction. And these, however, still have special dielectric properties. So the electric field, if these materials are exhibited to an electric field, then the electric field can influence the atomic charges in the material. And this basically gives some feedback onto the um, electric field. These dielectrica, they contain atomic charges which can be influenced, but they are not freely movable. And then the E field, which is acting on the dielectric material. So then you have either atomic dipoles, which are generated, or they can already exist, and then they will be ordered by the dielectric material. So, for example, you have some atom with some positively charged nucleus. You always have some electrons orbiting around this nucleus, and if it is brought into an electric field, then it can be that you basically you have this cloud of electrons and you pull the electrons a bit towards one side. You could imagine that, so they lean, then they are they're not fully balanced in the sense that this atom starts to build up a dipole moment. It could be also that whatever particle or whatever um, um, that the material has already inherently some dipole moment inbuilt, and then it can be oriented out in the presence of an electric field. These molecules start to orient themselves, and that will counteract the electric field because yeah, you have charge that is aligning due to the electric field. You have a dipole moment which is aligning due to the electric field, but also this particle with this dipole moment, of course, it brings in its own charge, and that is then usually reducing the electric field that you have. So, for example, if you have here your nucleus, and then you can think of, the nucleus is very, very small and confined. The nucleus has just is an ordinary on magnitudes smaller in size than the atom. Uh, as such, the electrons are orbiting in quite large distances, large in comparison for the atomic scale. They're orbiting here around this nucleus, and you have hence an atom, or in general, you have atoms which are consisting of all of them of positive and negative charge. So conductors will have electrons which are free to hop from one atom to the other. But non-conducting materials do not have that. The electrons are bound to the nucleus, and there can no charge occur, no charge transfer, no conduction can occur. But what can still happen is that if you have this cloud of electrons here, that they can be slightly pushed to one side and leaving that whole atom here a bit unbalanced in the sense that it has a dipole moment after that. And yeah, that is what you consider an electric polarization. Also, it could be molecules that are inherently not balanced in the sense that if you look at them, they already have inherently this dipole moment. Also, those are polarizable. And once you, so this would be the second case, basically, you already have inherently an existing dipole. Once you apply the electric field, you will orient this dipole, and that is what we consider a polarization. So that would be the case where you have here elements you see in that atom that I depicted over there. You have a positive charge in the center. You have electrons all around. But if you are going a bit outside, this whole is balanced. There's no um, 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 also the force, the electric. Uh, if you think of the force field between these positive and negative charges is such that it does not extend beyond um, the size of the um, atom then in that sense. But I mean, it's a bit difficult because this is a very classic view also, and at the atomic level, you have to be then a bit careful, but I think it is a valid way to look at it. Now you can have these molecules, and you see already here the plus is here on one side, the minus on the other side. So it's clearly, it exhibits a dipole moment, right? And if you have an electric field, sorry, this should be rather straight lines here, then you see these little bubbles here, these molecules, they might have been oriented arbitrarily, but once the electric field is present here, they will align in accordance with the electric field. So the minus goes here, point the where you have the minus located, that will tilt here to the right, and the plus will tilt here to the left, so that these are oriented. So you get this is here basically a dielectric material, and the atomic dipoles that I have sketched here in green, they are generated due, or they are either generated, respectively, they are oriented according or due to the electric field, or they exist in the first place. They already exist. It could be also an option. But then, in the presence of the E field, they are oriented. So what you obtain here is polarization of the material, and you see the polarization that counteracts the electric field. So you have a polarization field. This is kind of like a secondary electric field or a contribution to the electric field due to the orientation of these molecules or atoms. You have a polarization field P and R. And this is counteracting, so it is an opposite direction, opposite to the external E field. And this P, this polarization field, is superimposed to the electric field. So inside, this is happening inside the material, right? Outside the material, there will be no effect due to the dipoles of inside the material. So the material, the E field, if you have an E field uh, in some space and you bring in some part of that space an electric and dielectric material, the um, polarization field will build up only in this dielectric material, and only internally to this dielectric material the electric field will be basically counteracted and will be reduced. So that means a material total E field is weaker than in the absence of that material. And actually, this is actually already taken into account in Coulomb's law, within the material, because now you have to bring in the charge contributions of the charges within the material into the Coulomb equation here. But if we Coulomb's law inside material, so if you look at the force is being then reduced by this epsilon relative compared to the force that is present in vacuum. So your Coulomb law is 1 over epsilon r times the charge 4p epsilon E naught, summation of all the contributions I running from 1 to n. So this force is a force in vacuum, yeah?